And now it's my pleasure to welcome Ion Stoica. He needs no introduction, but Ion is a professor at UC Berkeley. He's also the executive chairman of Databricks and Anyscale. And he co-founded multiple open source projects that you all use, like Apache Spark, Ray, VLLM. And he co-founded 4 companies, LM Arena, Anyscale, Databricks, and Conviva, just like that. And he's also a fellow of both IEEE and ACM. Ion?
Thank you.
Hey, Ion. My first question is, where do you think innovation is happening nowadays? Because we have these huge companies, huge startups like OpenAI and Anthropic, and big companies like Google and Microsoft and Meta doing all this research, but yet a lot of the big innovation that all the developers are using here, like VLLM, come from your lab. Are they coming from students? What's your secret? How is academia coming up with all these ideas and not the big labs?
I mean, there is no secret. You get good students and let them run. So that's kind of pretty much what it is. I think that it's a good question, and I'm hearing that question a lot. So one context I'm hearing that question in, say, hey, you know, like for instance, for, as I say, for pre-training, all the innovation come from industry. Right? So, you know, like, because, you know, academia, they ask, you know, we ask for more resources and so forth. Say, why do you need resources and what can you bring to the table? Because again, look, all this innovation, transformers and everything almost come from industry. So my answer to that is that, look, that's kind of unfair question, right? Because it's like asking you, you know, why didn't win the game? And you cannot even participate in the game. But wherever we, you know, the academia can participate, I think there is a lot of innovation coming from academia, obviously, as always, also from industry. So that's why if you look at inference, so for inference, you don't need as many resources, right? A lot of innovations are coming from academia. It's not only page attention, it's flash attention, spec infer, all of this, and a lot of speculative execution algorithms and things like that. So that's kind of the proof is in the pudding, right? So of course, for the pre-training, it's a little bit less from academia because there is lack of resources to do, you know, all this kind of research at scale. Hopefully that will change. But this kind of will be my answer. So I think that in some sense, not having also academia participate on, you know, more actively on pre-training, I think that we all lose.
Okay, so basically you're telling us we need to give more resources to your lab so you can innovate in training as well.
And to other labs as well. You know?
That sounds actually good.
Everything we do, like for instance, you know, it's open source and you know, everyone can use, and I think that the key things about the open source, like other projects have demonstrated over and over again, not only from academia, but obviously PyTorch, you know, Kubernetes and so forth, is that it provides you some shared artifacts on which everyone can contribute, and they can build on top of each other, rather than having, you know, this kind of silos where everyone is doing almost the same thing. And I think that it's not as effective use of human capital from the society perspective.
That's very good. I'll talk to Lisa about that. So my second question is about kernel writing. So that's really a big deal for companies like AMD and NVIDIA. We have thousands of engineers writing kernel because every time we have a new GPU, the memory hierarchy is different, so you need to rewrite the big kernels like the gems and so on, and pretty much manually optimize them at assembly level. How close do you think we are to LLMs that can write code that are equivalent to human expert level code? Because that would be a big change for us.
So I think that we are making progress. And I'll tell you at the end what is actually the biggest challenge in my mind. But just to give you a sense about, we did not necessarily writing kernels, but we did a study at Berkeley over the summer in which we asked students to apply some of these tools to their own research. And this was more tools around like Alpha Evolve. There is an open source version, Open Evolve. And this is basically what they do for people who, how many of you know and use Open Evolve? Okay, so basically what it is that if you have a simulator, right? It's working also for the real system, but like you have a simulator and basically say a load balancer, like expert parallels load balancing, right? So you have a simulator and basically you have the policy you want to optimize and you basically say, okay, I want to optimize this for this policy, start evolving and evolving. You are going to say, okay, how you are going to evaluate the new policy? Well, you are going to run this, the simulator and on these traces, and these are the outputs, and these are the outputs you want to optimize, like throughput and so forth, or imbalance factor and things like that. And then this is what you give. You give to this kind of like Open Evolve, you give the simulator code, you give the statement of the problem, how to evaluate it and so forth, and then it's an evolution process which iterates.
So it's like RL for a verifiable domain?
It's actually RL, it's almost, like you see like, but anyway, you do the evolution, I'll answer that question, and then you end up with a policy which is coded in the simulator, which hopefully is better than what you started with. And I think we did like around 12 projects. And 7 of these projects, they're describing policies or algorithms which are, their work published in top conferences in systems and AI. And the other one were work in progress or submitted papers, but not yet accepted. And in 9 out of 12, it did better than state of the art, right? Now, let me answer the question about RL. It's not exactly RL. So when you do this kind of rollouts, right, you are doing a change and you do these rollouts to see how well the new solution performs, there are 2 things you can change, right? One, you can change the model, which was used to generate the solutions. That's RL, right, updating. But the other one, you can change the prompt. And in this case, the prompt is what is changed because the kind of simulator is part of the prompt. And so it's not the model, model is not changed. And you change only the kind of the prompt, the new solution, you iterate on the solution. And this is nice for 2 reasons. One, is that you can use the state-of-the-art models, LLMs, right? And it, by the way, is quite cheap. In our case, it's all a few tens of dollars. This is how much it costs. So it's very effective. But the other thing, and what is the difference between updating? Of course, you can update both. You can update the model, you can update the prompt. By the way, updating the prompt is like, it's a form of in-context learning. So it's still, learning. But one thing about this kind of updating the prompt and things like that, you can get a much richer feedback, right? You can get a feedback, I ran the program, I got this one, maybe these are the logs and things like that. While with the RL, you get typically only one kind of value, a scalar, or in some cases, 0 or 1 is true or false, a binary.
Theoretically, it's possible to use a frontier model by just iterating on the prompt and generate good
but
code
in this
for
prompt is a solution. Yes.
Oh, that's very interesting.
So this was, so now going back to your, to what you asked, the key for this is to have a simulator to have rapid iteration, right? And because like these are not very sample efficient. You are going to explore the space. So having something, that's why I was thinking about simulator and not, you can do on the real system, but it will take much longer, right?
So do we need to provide you a simulator of our GPU?
It's actually, this is also the process most of the research is going. It's, in general, you do develop a simulator if you can.
Okay.
Because it's faster even for the human to do the iteration and do the real system. But it will be great to have an accurate simulator. Now, let me tell you what I think, and I think it's one of the biggest challenges with generating the code. It's one of the biggest challenges in generating the code automatically is that, forgive me to say, but the entire stack doesn't work as expected, right? Mm-hmm. There are actually still a lot of documentation, which is, I'm not commenting about AMD, I'm commenting in general about accelerator. It's inconsistent about how, the documentation is out of date sometimes, and there are many bugs at all levels. Firmware, all levels of the stack and things like that. It doesn't work at scale as expected, right? And so that's kind of the things, and it's everyone has these challenges. So then it's very hard to develop a solution if the stack has, kind of, so to speak, unexpected behaviors, right? So in some sense, you need to learn. Probably one solution is to learn, how the stack is behave at a given time for a particular versions, everything from the hardware all the way to the stack, and then try to develop solutions. I think from everything I've seen, that's one of the biggest challenge.
Very interesting. I have a question on data, because earlier this year there were articles on, we have the scaling laws, but we don't have data anymore. We run out of text data, right? The big frontier model have already exhausted all the available data. But then we started to see synthetic data, but isn't synthetic data just the same data being reshuffled? And then we start to see chain of thought, and isn't chain of thought also using the same data? But it's actually somehow working because LLMs are getting smarter and smarter, and just like a few weeks ago, a couple of them got gold at the IMO, the International Math Olympiad. So obviously, they're becoming a lot more intelligent based on the same data. How does that work?
Yeah. So first of all, again, large language models, obviously, it's amazing technology because fundamentally they do encode all this kind of human knowledge, right? This is what they do, right? It's like by predicting the next token in a kind of statistic manner, they encode all the human knowledge. Now, at some point, if you run out of human knowledge, it's not much more you can encode. So that's kind of the intuition about why running out of data. But because a large language model exactly this is what they do at the high level, right? Now, they get surprising results, but it doesn't mean that the mechanisms what they do is different, right? It just so I think there are a few things here about the kind of data, yeah. And one, you are talking about the synthetic data. So synthetic data, I think we discussed earlier, is like basically you have in a domain, you don't have a lot of data points, right? So what you are going to do, right? What you do is basically synthetic data in some sense, in this case, this is some kind of interpolation, and you add more data in that space, which is consistent, which data you are going to have. And why do you do that? Because you want to reinforce, that's an important space, data space, and you want to reinforce that when you train the models, right? Actually, even before that, when you train the models, when you pre-train the models, you are going to reweight about different kind of data. The higher quality data, you are going to present multiple more times to the model to learn, and you're putting in the batch than the one which you think it's a lower quality, okay? So that's kind of what it is. But I think that the other aspect you are mentioning with RL and everything like that is that with RL and this kind of post-training, the one thing it's very important is that it can generate genuinely new data, right? Because if you are going to have an agent, which is an LLM interacting with the environment, so interacting with a web, right, or something like that, you are going to generate new data, right, from these traces and from this interaction to the environment. And this is, I think that's one of the biggest advantages of this post-training RL in particular.
That's great. I have a question about transformers in general, because when transformers got invented, immediately people said, this is not scalable, it's quadratic. Even some of the godfathers of AI have been saying that, right? Transformers are not the way, they're quadratic, and they're stupid, they just guess the next word and all that. But again, we see them becoming so smart as winning gold at IMO. And is it really quadratic? Because to me, they're becoming faster and faster. What's going on?
Lynn can tell you more about how they do.
And maybe Lynn can share some thoughts as well.
Yeah, but fundamentally, yeah, in theory, it's like attention layer. It's quadratic, but in the last 1-2 years, there is a lot of work on sparse attention, right? In general, and you have window-based attention, top K, and it's a lot of different ways to do attention, and actually
multi-latent attention.
Yeah, and actually even now many models actually they don't do full attention at every layer, right? From starting with even open source with Gemma and things like that last year. So it's like they try to break that kind of quadratic overhead.
So are we effectively near linear with attention with all these techniques?
Yes. In many cases, yes. Still, probably you have a combination, some layer quadratic and so forth, but definitely much better than quadratic. And I don't think any reason to not this to become better. And if you think about even things, older technologies like RAG or something like that are in some sense to break a little bit.
That's
to
right.
make it more, at least the prompt smaller, right? Because with this kind of 1 million context lengths and so forth, you can have everything in.
Right.
But yeah.
So do you feel we need to move to something else at all? Because there are some organizations are researching like symbolic graphs and rule-based and hybrid architecture. Do you feel we need something new, or we still have a long way to go with LLMs?
As a researcher, I hope there will be something new. But to tell you the truth, it's like with all you see is like we see this kind of we have this technology which is working pretty well, and now people try to optimize all the way from you guys, right? You are going to optimize the hardware for transformer, right? And to the model, architect, designers, and everything. Inference and
serving
and training and so forth. So you have to have a new technology. If it's a new model architecture, it's going to be 10x better at least, right? Because otherwise you are going to go with this one because you are continue to optimize. This is what we know how to do it, right? This is a history of the microprocessors and everything, right? It's like we didn't look for other technologies or architecture, although in theory they could be better, right? It's like, every now and then I was hearing about the analogic chips, how good they are, right? It's like, and they, they're much more energy efficient, all of these things, right? But it's very hard. It's very hard. Now, the things about, I do think that actually you'll need to have, you need to marry more and more, and it's already happening. This kind of neural network like transformers is more kind of rule-based approaches, right? Like some symbolic work you talk about. Because I think that we as humans, obviously, we have this, type 1 and type 2 learning. But we learn a lot, and we have a lot of knowledge about the world already when we are born with, right? We are wired, right? Already, pre-trained, so to speak. But as you go and you grow, a lot of things you are going to learn by rules, right? If you think about when you go to college, when you learn, when I'm teaching, right, later today, what I'm telling I'm telling students, a bunch of rules, right, which they should internalize. And rules is a very effective way of encoding the information. And we are discussing, just to give an example about, and this is happening, actually coding, it's basically, it's a bunch of rules at the end of the day. And this is what I was saying is that, many people give examples about this kind of, for planning problems, about the limitation, try to use planning problems to illustrate the limitations of these large language models, and basically saying, Tower of Hanoi. They cannot solve it after, no matter how big, how good the LLM is, after a while, if you just increase the size of the problem, it's going to collapse. Right?
We would collapse too.
Yeah. But if you ask the LLM to generate the program to solve the Tower of Hanoi, so the rules, right, to solve that Tower of Hanoi, then once you have that program and you use debug it at a small size, problem sizes, that can solve any problem size, right? So that's kind of illustrate, at least in my mind, why you need, and it's at the end of the day. So basically, what I'm trying to say here, instead of the LLM solving directly the problem, the LLM can generate kind of the rules, the program to solve the problem. And in many cases, it's more efficient. Exactly what we do as humans, right? We generate programs to solve the problems, not we don't do it directly.
My last question, I think the audience will be very interested in that. You've created incredibly successful companies. If you had to create a company right now, today, what would you do?
I think that two directions I cannot say, as a two direction, I still think it will be infrastructure, because I think that it's a huge challenge, right? It's like the complexity has grown so much in the past decade, both at the infrastructure level, where you have this kind of very sophisticated heterogeneous clusters. And it's not only in the accelerators, more recently it's in the networking stack and so forth. And then the software is going to be more and more complex, from kind of very regular applications like data processing or training, data parallel training and so forth. It's much more irregular with reinforcement learning and things like that. And so it's a big gap, trying to support these more and more complex applications, and then more and more running on more and more complex hardware. So I think it's still a huge amount of work to do here. And at the high level, at the application level, I do think that probably one of the main challenges is about building reliable AI application. By reliability, I don't mean like software reliability or hardware reliability. It's like in the sense that they should do what you expect them to do.
That's very good. And just maybe a last one. Instead of building a new company, would you consider joining AMD?
The one thing I learned so far, I'm old enough, never say never.
Okay. Thank you so much, Ion.